All right, welcome to a new week. So let's finish up these slides on algorithm analysis today. And we were getting ready to actually go and analyze algorithms. We were talking about analyzing functions before, mathematical functions with like big O, big omega, big theta. That's the cool one. And now we're ready to represent our programs, represent the complexity of our algorithms as those functions, and now it's all going to come together. Okay, so let's talk about some terms that you should have seen in 41, but we're going to define them again. Okay, so computational complexity, that's just the resources that your program needs in order to run. So, for example, maybe you have only an hour to use the computer because you have to go to work after, or something like that. Computational complexity is going to tell you if it's worth working right now. Okay, maybe it needs more than an hour to run. That's the idea. So it's just resources in a very vague sense, because money is a resource, for example. Maybe you require some amount of food in order for the computation to succeed. Who knows? But usually we talk about two that are very important, the most important. Time complexity. If we had to pick between time complexity and space complexity, those are hard words to say for some reason, we care most about time complexity. So we're like, okay, our program runs in 42 minutes, time is money, can we have this? Because then we can run it twice and make twice the amount of money, maybe. So that is the amount of time that an algorithm needs to run. And usually, though, we don't like talking about it in terms of time, like physical clock time. We think about it in terms of the basic operations, basic is in quotes, that the computation needs to perform. Okay, so we'll talk about that. Don't worry, we'll get into that. But we care about it like this because every processor is different. Like maybe my processor runs at 1.5 gigahertz and yours runs at like 3.5 gigahertz. Then, yeah, it's no contest. This one's going to win, but it was running the same algorithm. We need to be able to talk about the same algorithm running on different kinds of computers. We want to talk about its time complexity as one number. Okay, that's the idea. Space complexity is the analog of time complexity. It's just when you're caring more about memory. Okay, you want to know the memory that's being used when your program's running. Maybe you have an array that was given to you by the user, and you don't know up front how big that array is going to be. So you got to make sure that you can cover all your bases. So normally you count the number of like bytes that you use to store things. Okay, because that's the same across machines, right? That's the idea. We want to somehow talk about the same thing running on every possible computer that ever existed and ever will exist. That's the hope. Okay, so I guess the key idea is we want to come up with some kind of function, mathematical function, because then we can apply all this stuff that we can use to describe how when the input size varies, like the user gives us 4 things versus 24 things, how the program changes, okay? How the resource use changes, okay? Because obviously I think you can see that the memory use is going to be bigger across these calls, but if you have to iterate through this entire array, you're also going to take some more time to do that, aren't you? So we usually have a variable that represents the input size, okay? And then finally, because we have a function in terms of a variable, hey, we can do our asymptotic analysis. Aren't we cool? All right, so let's do an example. Let's analyze the running time of summing all the elements in a vector. So this is a very, very simple idea, and we're going to come up with a formula based on n, where n is the size of that vector. And we're going to count the number of basic operations. Okay, this is where I introduce that term to you. We're going to say that a basic operation, it's something like an assignment, it's a return statement, it's a mathematical operation, a variable lookup, things like that. It's hard to talk about a basic operation when you haven't taken CSCI 45 yet. When you have taken CSCI 45, a basic operation is just one assembly instruction. But we're not there yet. So I want you to think about basic operations at a higher level. Okay, essentially a basic operation is more or less a line of code that doesn't do anything silly, like call call a function that itself starts looping, because in the end, everything's going to go away. Every constant time thing is the same in the end, at the end of the day. So we can think about it that way. So for example, this is a constant time operation, this is a constant time operation. You can think of all these lines as taking, okay, this takes one basic operation, this takes one basic operation, things like that. Okay, so let's talk about this function now in terms of this. So we're getting a vector v. That vector v has size n. All right, and let's use n to determine how many basic operations are going to be performed inside of this function as it runs. So the first line we're going to execute is this one, int sum equals 0. So we're like assigning something into a variable that is one basic operation. Okay, that's the idea. Then we have this line, int n equals b dot size. So we're putting a value into a variable. Okay, so we can think of that as another basic operation, 1 again. And now we have to talk about this for loop, and this is how we're going to end up with an n in our formula, because this for loop's going to iterate a bunch of times. The first thing that's going to do is this line. It's never going to do it ever again, so this takes one basic operation for this line, okay? And then the rest of these are going to get repeated, so we have to talk about those in a different way. So let me put a box around them. Whee! So the next thing that happens is, well, we need to check this condition to see if we execute the body of the loop. So that takes time. We have to get this variable, look it up, variable lookup, hey. We have to get this variable, look it up, and then we have to compare them. So this is kind of, we can think of it as 3 basic operations to perform this comparison. Okay? This is all very hand-wavy. You can call this one basic operation if you wanted to, because constant time makes everything go away, right? And then we execute the body if the condition is true. All right? So then we do this. Sum equals sum plus v at I. So we got to go somewhere, one basic operation, add it into sum, and then store it back into sum. So that's another 3 basic operations, let's say. Okay? And then finally we increment our I, which is I equals I plus 1. There is a mathematical operation, there's a variable lookup, and then there's also an assignment. I equals I plus 1, right? So that's, let's say, another 3. So this is all going to continue. These are all going to keep getting repeated, and then we're going to finally compare this thing, and it's not going to be right anymore. It's going to fail, and we're going to jump out of this loop and return sum, which is a return statement that is one basic operation. Okay, you never have to do it this pedantically ever again, but I want to show it to you like this first. So the number of basic operations that are going to take place is going to be up here, 1 plus 1, okay, that's 2. Eventually we're going to get down to here, so that's plus 1 over here. And then we need to consider the loop. So this happens once, that's 1. And then all of this, think of how long it's going to take, right? How many times is all this going to get repeated? Well, I think you can imagine that this is going to happen for every element of the vector v whose size is n. So this line gets executed n times, which means this also gets executed n times. That's n times 3 plus 3. And then the comparison, though, it gets executed also, yes, every time the loop gets executed. So there's another 3 inside of there. But it also gets executed one last time before the loop stops. So there's another 1 right here. It's a hidden kind of. And then finally we return our value. That's the 1 over here. So if you spell this all out, it's 3, 6, 9. So that's 9n plus, let's see here, 9n plus 2, 3, 4, 5. 9n plus 5 basic operations. That is our formula. Okay? And then we can give this formula, like this is f of n, to like big theta. And we can say, okay, what's the big theta version of this formula? How is it simplified? What is it asymptotically doing? And the answer is, well, it's big theta of what? Big theta of n, yeah? And that is the real shiny answer, and we call that linear time, okay? Hopefully this is all coming back to us. So that was a long, in-depth example where I tried to show you the nitty-gritty of counting all this stuff. But the truth is you don't ever have to do that, okay? Because this is like, this is all constant time. This is constant time being multiplied by n. It all goes away, okay? So you don't have to be very pedantic. You can just be like, okay, this is 1. This whole thing is 1 basic operation. Okay. Sometimes your algorithm works differently depending on its state. So you can't really represent everything in terms of just one function. We need multiple. So we think about our program running from different perspectives. We like to do the worst case, the best case, and the average case analyses. So the worst case analysis is when your algorithm, doesn't matter what the size is, nothing is going your way, and you're taking the most amount of time / space. Like everything sucks for you this day. That's the worst case. And usually you need to worry about this the most in your program, because eventually, given enough time, you're eventually going to hit the worst case, and you better know how bad things are going to go when that happens. Okay? The best case is usually the least often one you care about. It's when everything is going your way and you take the least amount of time / space when you're doing something. Not too bad. Usually it's constant a lot of the time, your best case. And then average case is in between. It's you average together every possible outcome, the best cases, the worst cases, and every other case in between. All right? So normally, the average case is taught to you in like an upper division algorithms class, and so that's what I'm getting you ready for. We might do a little bit of it, but not too much. So my best example for you is binary search tree search. So the idea is you have some value v that you're looking for in your binary search tree. Maybe it's like 42 or something, and this is a variable. The state of the tree is a variable. All you have to work with when you're trying to come up with the time complexity is, well, how big the tree is. That's what your n means, okay? How many nodes are in it, okay? So that's what your n means, and you have to somehow use n to talk about the worst case, the best case, and the average case. So let's talk about the worst case running time for binary search tree search. So let me give you a tree that doesn't look like this. Let me give you the worst possible tree of size n, or n is, I guess, 4. Okay, so this is the worst possible tree of size 4, and I think you can imagine, like, if it was size 5, it would look like this. It's essentially a linked list, so tree is list. And also, the thing that you're looking for is not there. Value not there. That's the worst case, because you have to search this node, this node, this node, this node, this node, and go right once more, and oh man, it's not there. Okay? Hopefully this algorithm is coming back to you. That is the worst case for binary search tree search. You have to compare 1, 2, 3, 4, 5, n times, and notice that eventually you're at the end. So that's like n plus 1 times, because you got to check for null. So that's horrible. N plus 1 comparisons. And that's essentially your algorithm. You just keep searching n plus 1 times. And so, in the worst case, a binary search tree, if it's unbalanced, it has theta of n complexity. Okay? That's the idea. Now, the best case is very, very easy. That's when everything's going your way. So you're searching for, like this is your root, you're searching for 8. Okay, that's your value you're trying to look for. You only have to compare once. That is your best case running time. It is constant time. O of 1, big theta of 1. Yeah? And then the average case is you average together everything. And this is beyond the scope of this class, but you can imagine that the average tree is balanced, and so the average height is logarithmic, and so the average case running time for BST search is big theta of log of n. Okay? So this is my hand-wavy argument for average case, but I hope that the other two made sense. Okay. So now we're getting the hang of doing this in a mathematical way. Let's analyze code that we have written before. Yeah? So is prime, calculate pi, sat solve even. Hey. So let's talk about these. Well, let me give myself some space, actually. So is prime, first of all, what were you doing with x? You were iterating, right? The algorithm looks something like for I equals from 2 to like x maybe, if you were doing it the naive way. The less naive way was square root of x. You only had to look up to square root of x because you were searching for just one factor. That's all. And then you can like check if x, or sorry, I times I equals I, not I times I, something like I divides x, right? That's what we wanted to check. There we go. And if true, you return false, if so. And then once you're out of this loop, if you didn't ever return, you return true. Yes, it is prime. We didn't find a factor. So I think you can see that this is now, let me use a different color. This is constant time. This is constant time. This is a constant time thing, checking. This is where the work happens. You got to iterate through. You got to do this body how many times? Well, square root of x times. So it's essentially square root of x times 2 to do this green box right here. Okay? And that's where your complexity is going to come from. Okay? So the 2 doesn't really matter. The 1 down here plus 1 at the end doesn't really matter. This all goes to big theta of what? It's actually square root of x this time. Yeah? That's the idea. It's like, it's essentially, it's not x squared, it's x to the 1/2, and so that stays. You can't get rid of the power, okay? That's why it's square root of x, which is less than linear time. That's quite nice. And then similarly, calculate pi. What did you do? Well, you threw num darts times, right? You do num darts times, pick a random x and y coordinate, and then you check if it's inside the unit circle. Inside the unit circle. Okay, then that was it. You did this a bunch of times, and you kept track of like whether it was, whether it wasn't, like add to count, and then you eventually like return some value over some other value. Yeah, that's essentially your calculate pi times some other thing, times like 4 or something, right? So this was your algorithm, and notice that all of these things in the body of this loop were constant time. It was a lot of work, but it was all constant things. There was no looping involved there. Essentially, you were doing the body, which is like, I don't know, some number of constant things, so that's O of 1, big theta of 1. You were doing it num darts times, okay? And then you're returning this. That was another constant time thing. So you just needed to multiply it by num darts. So I hope you see that. This is big theta of num darts, which is my long variable name, because it's a loop where you're doing constant work inside of it. Okay? That is the idea. And SATsolve, that's the fun one. Okay? That's where things go a bit weird. The idea was you had a bunch of variables like x, y, and z, for example, and you tried all the possibilities for x, y, and z and saw if they satisfied the solution. You tried 0, 0, 0. You tried 0, 0, 1, where 0 is false and 1 is true, right? You tried 0, 1, 0, 0, 1, 1, dot, 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 all the way down to 1, 1, 1. And for each of these, you're evaluating the formula, which you can imagine that the formula stays the same each time. And so essentially, you were worrying about the variables inside. That was your bottleneck. You're doing constant work for every value of a variable, okay? For every choice, for every single variable. So how many of these are there? Where let's pretend that the formula has n variables. How many? Well, I think you can see that it's 2 to the n. Ho ho. So SATsolve was doing this much work was doing constant work, sorry, this many times. Okay? And so that we get to prove that the satsolve function was working in exponential time. Unfortunately, the answer is big theta of 2 to the n, because you had to try every combination of all of the variable values, and there were 2 for x, 2 for y, and 2 for z. So you had to do 8 different possibilities. Okay, and that blows up horribly. That is exponential time. Life is no fun. That's one of the worst you can have. Okay, so hopefully this is all making some sense. Please yell at me if it's not. We're just getting more practice from the kinds of processes that we learned in CSCI 41, and now hopefully that we're doing it again, it's making even more sense. Okay, that's the idea. So that brings me to this table now. So this is from your book. It's wonderful. It's more or less accurate. Let's pretend that one instruction in your computer, like one basic instruction, whatever that means, takes 1 microsecond, which is 10 to the negative 6 seconds to execute. Actually, a lot of your computers are a bit faster at this than this. It's more like nanoseconds for a lot of instructions, but because we access memory all the time, it kind of gets slowed down by that. Okay, so that is why we're going to pretend that it takes a microsecond to execute every instruction rather than a nanosecond. And here are some common functions. So if you have a function that is theta of log base 2 of n, if you have n things to work on, and that n is 10, then your program is going to take 3.3 microseconds to work. Okay, that's the idea. If n was 50, it's going to grow logarithmically, and so it's still, when n is huge, like 100,000, it's not going to take very long to do much, okay, to do your entire algorithm. So, for example, binary search on a sorted array, it's really fast, even though you might be searching through a ton of things, okay? And then we go to linear. That's slower than logarithmic. It takes more time. So if you have a theta of n, a linear time thing to work with, then notice that this is all going to be a bit slower. So you're going to get down to 0.1 seconds to go through 100,000 things. Oh man, so much time. And this gets bad eventually, once you get bigger and bigger. N log n is a standard sorting algorithm. It's the best sorting algorithm for general purpose sorting. They exist in n log n of time, and suddenly we start getting into real seconds. It's still pretty fast, but now you're multiplying n by log of n, and that's making it take more time. Now, n log n is kind of like where you want to stop. If you could, never write a program that has a complexity worse than n log n, because the second you try to scale your giant software as a service that you're selling to people online, that's when it goes bad, okay? 10,000 takes 100 seconds. 100,000 now starts taking hours, okay? That is no fun. That is unfortunate. And then n cubed is pretty hopeless when you're trying to do a lot of things, okay? So you want to stay small if you can when you have algorithms that can't be improved past this, okay? And then exponential, you don't even want to know. N equals 50. If I tried to have your satsolve program, if I tried to give it a size 50 formula with 50 variables, I wouldn't have been able to give you a grade until you are in middle age, okay? So that is unfortunate. That is quite sad. It's super fast still when n is 10, but you give it any reasonable size, you're kind of out of luck, okay? So 10,000, let's not even talk about how many centuries that would be, okay? So that is the fun table of algorithmic complexity. You want to stay above this line if you can help it. N squared sometimes gets to join the party, not always, okay? That's essentially where you want to stop. That's the idea. Now you know. So here's a good question for you now. I'm going to give you this formula, this function. It's going to calculate something, and I want you to come up with the worst case time complexity for it. Okay, so first I'm going to go over like what it's actually doing, and then once you have an idea of how it works, you can go and analyze it. Okay, so it's going to get n things. It's going to get a sequence. So you can think of it as getting an array of n things, but the indices are suddenly starting at 1. That's the only weird thing. And then it's going to output one number, the value of the maximum subsequence sum. So what that means is this. Here is my example vector. 1, -2, 3, 5, -7. Okay? Here we go. And the maximum subsequence is you have to pick contiguous elements, so like the -2 through 5, maybe 3 through -7, and then you sum them. Okay, so the sum of 3, 5, -7, that's 1. This one is 6, and you're looking for the maximum one. You can try all the possibilities. You can try just one, you can try a couple, until you find the maximum, which happens to be this one. And maybe I'll use a different color for that. This is the maximum subsequence sum. It's 8. Okay? You can't do any better because you try to do more, like that makes it 6. You can go over here and get a 7, but that's not helpful. And then, of course, adding -7 to your sum just ruins everything, right? So this is the maximum subsequence. That is, you want to start at index 2, go to index 3, and go no more than that. That is what this function will return. It will return back 8, given this particular sequence. Okay, this particular array. Okay, so let's talk about how it's doing it now, because that's the key to determine the running time. So what it's going to do is, let me do like a simpler vector. This is A1, A2, A3. What it's going to do is start I at 1, so it's going to start like, let's start our sequences starting here, and then it's going to keep track of its intermediate sum. So right now it's 0, and then it's going to make j start at I, so you can go from here to here. That will be your initial guess. And then you're going to keep on expanding. That's the idea. Oh no, this is not allowing me to change it. So I starts out being, or sorry, j starts out being I, so you're going to start here, and then you'll continuously widen j to be like, okay, let's check if these two, if we sum those together, that's the best. And then you'll change j to be this. Let's check if these ones sum together to be a large number. And you're just going to keep tracking the maximum, okay? You're going to keep on seeing if your current sum between your current I and j are the best, okay? So it's going to keep on doing it like that, and eventually I is going to be 2 now. Like, okay, let's start our sequences here and see if like this one's the best, or maybe this one's the best. And so that's what j is looking for. It's trying to find the last place where we want to add to our sum, okay? So it keeps on trying with a new I and a new j. Okay, hopefully that's making some sense. I encourage you to code this up and see how it's really working, but hopefully that was good enough. And now I want you to try to analyze this, okay? And we'll come back and do it together. All right, so I'm going to copy it here and we'll talk about it. So this is constant time, theta of 1. This is going to execute its body n times exactly. Yeah, so this is n, theta of n, we could say, if we wanted to. This is a single thing, that's theta of 1, one basic operation, one instruction. This is going to execute an interesting number of times. That's the weirdest thing. So we'll come back to that. And then the rest of these is constant, constant. So this whole thing, the whole body here, is constant time, okay? Just a certain number of basic operations. And then finally at the very end, you return back something, so that's constant again. This, you can't just say is n, because when I is 1, the inner loop iterates yes n times, because I is 1. But when I is 2, it iterates n minus 1 times. Ooh. And then when I is 3, it iterates n minus 2 times. So that is unfortunate. That is quite unfortunate. We have no clue. We can't just say it's going to iterate n times because it doesn't. When I is n, it's going to iterate just once. So maybe we can think about this one separately. That's kind of the key here. So we can pick this one out. This is going to take theta of n time. Totally. We're always going to set this theta of n. But this one's going to be a bit different. Let's try and figure out, this is the main work right here, right? Let's try and figure out how much this gets executed, right? How many times that body right there gets executed. And it's going to be n plus n minus 1 plus n minus 2 plus ... all the way down to 1. Okay? That's how many times this is going to get executed. And because it's doing constant work, this is essentially the formula that we're looking for. Okay? Let's talk about this. So how many times does this get executed? Boop, boop, boop. That's what we want to count. How many times? Okay. So we've noticed this, and there is a formula for that, right? It's n plus 1 times n over 2, right? That equals n plus 1 times n over 2, which is something fancy. It's like, okay, n squared plus n over 2. So it's like 1/2 times all these, 1/2 n squared plus 1/2 n. But because we're doing big theta, we can transform that further to big theta of n squared. You see that? So now, finally, we can do our analysis. This line is going to happen once. That's theta of 1 still. This line, well, it doesn't really matter. It's going to, yes, increment I, but let's not worry about that. Let's worry about the body instead. Okay? Yes, it's going to increment I n times, so that is technically theta of n that we can add to. This line is going to get executed theta of n times, so it's theta of n times theta of 1, which is n times 1, which is theta of n. And then this bad boy right here we have just determined is theta of n squared. Yay. Okay? And then this one's still theta of 1. And so the analysis is, we add these all together. Okay, maybe I'll choose even a different number. So it's theta of 1 plus theta of n plus theta of 1, or sorry, plus theta of n plus theta of n squared plus theta of 1. That is the running time analysis of this whole darn thing. Okay? And who wins when you add these all together? The answer is n squared. Okay? So the whole darn function, the whole darn algorithm is theta of n squared. So technically, you are allowed to think of this as iterating n times if you know the trick. But we had to discover that this, yes, it is going to actually multiply n by n a little bit. It's still less than n squared, because there's some halves there, but now we know. Now we know that the asymptotic analysis of this whole thing is theta of n squared. Okay? So that's my fun extended example of algorithmic analysis. And now I want to switch gears to what's known as finite state machines. Okay, it's a fun little thing. You are here. Push-down automata and Turing machines is something you don't really learn about in this class. It's an upper division thing. Though your book does have a chapter on Turing machines if you're interested. Do feel free to read it. I don't think I will be testing you on it, though. I'm just going to test you on finite state machines, because you're ready for that now. So a finite state machine is just a nice way of breaking down an algorithm. It is a way to model how something works, how some system works, we say. And it's quite nice because we can think about it in terms of states and transitions. And that is wonderful. That makes things a lot easier on our end, because a lot of real-world processes work like that. They have states that they're in, and they transition between those states. Okay? So let's talk about what a finite state machine needs in order to work. FSM for short, of course. They need what's known as a start state. So these circles are states. Okay? These circles are states. And we need to say, when we power on the machine, where it begins. So we put a little arrow to say the start state. Okay, you can even label it with start if you wanted to. And potentially, some versions of finite state machines, they have final states or accepting states. So for example, if you're looking for even numbers, the even state will be your final state. That's where you would like to stop. Okay, that is the idea. You would accept an even number, but not an odd number. That's how we say it. Okay, don't worry, I'll get into some examples. Also, a finite state machine could potentially output things. Like you give it some values, give it some inputs, and it's going to give you an output along its transitions. Okay, so let me explain this one. This finite state machine that accepts only even binary strings. That's this thing right here. Let me explain how it works and why it's working. Maybe I should make a new slide just so that we have room. You have no idea how long it took for me to draw this in PowerPoint. Okay, so this is going to take input as binary numbers. The things along these arrows are the potential inputs you can give, so you can only give zeros or ones, depending on the state that you're in. Oops. So here's the idea. You can give the binary string 0, 1, 0 to this state machine. And let me walk through how it's going to execute. You're starting here, and then you give it a 0, okay? So you're going to follow this transition along the 0. It like eats up the input, and it's like, okay, I'm going to remain in the even state. That's the idea. So it goes, once it reads this, it's an even. And then you input the next bit. So you're in this state, you input a 1, you follow the 1 transition. Okay, now you're in the odd state. You see that? Now you're sitting right here, ready to take more input potentially. Then you take a 0 input, bam, and you're back in the even state. And that is an accepting state, which means that if you're done now, the finite state machine's like, yeah, cool, this was an accepting state. The number that you gave me was even, and the number was in fact even. It was 2. Yeah. And what it's doing is it's remembering what number you're at, essentially, every step of the way. The number 0, if you just gave the 0, that's 0 base 2. That's equivalent to 0, right? And so, yeah, that's even. So if you were to just stop there, that's why it keeps you in the even state. You see that? If you gave 0, 1, base 2, that's 1 in binary. That's why it brings you into this odd state, because your number so far is odd. Isn't that cool? And then if you gave it like another one, if you gave it 1, 1, you'd follow this one and stay in the odd state because that's 3, right? That's equivalent to 3. Isn't that crazy? So that's how it's working. And if you just gave another 0, that would be 3 times 2, which is 6 now, base 10. So that would be 1, 1, 0. It is even. Any number that ends in a 0 is even in binary. That's essentially what this is keeping track of. Isn't that cool? That is how you use a finite state machine. And I think it's helpful because you can totally program this very, very easily. You're like, okay, you have some variables that keep track of your state, and then you have a bunch of if statements that take the next piece of input and transition you across states. So that's one. Now let's talk about outputting finite state machines. So here's a fun one, a fun little example of like maybe an old-fashioned soda machine or something. This one would look like this, and let me put it in the back. There we go. It starts here, and the idea is you give it inputs. The inputs are here. These are inputs. But it also has outputs along every transition. So you give it 1 nickel, it gives you nothing. Yeah? It wants a quarter. All right? You give it a second nickel, you give it 1 nickel, now you're in here. It has 5 cents that it's saved. It knows that you have given it 5 cents total so far. And then if you give it another nickel, the vending machine goes to this state. You see that? It's keeping track of how much money you've given it. And still it's giving you back nothing. You give it a third nickel, you've given it 15 cents. Oh, and then you're sitting in this state. So finally, you end up giving it one more, you're in the 20-cent state, you're still getting back nothing. But the second you give it another nickel, it's going to start giving you back things, okay? Maybe this is the wrong kind of transition. Maybe it should be this one. Go back to 0, because then no matter how many nickels you give it, just 5 cents at a time, it'll keep giving you back soda. But who cares? This was what was in your book. So here is the idea. You give it one more nickel, and it starts giving you back stuff. It gives you back soda or something, okay? That's an output, okay? So there's no concept of accepting states in this one because there's no need for it. It's like it's just going to do something. It's like it's the void function equivalent of a state machine in a sense, okay? So that is finite state machines in a nutshell. Let me show you how they're mathematically defined. And this is not too bad. It's just you have to keep track of all the little things. So a finite state machine, we say it's a 5-tuple, and we give those tuples specific names: Q, capital big Q, little q naught, I, A, and delta if they are ones that have accepting states and non-accepting states. If you have finite state machines that produce output, you have to like get rid of the accepting states maybe and change that for something else, and yeah, so on and so forth. The idea is that all of these are necessary and they make sense. So Q is all the states that you have. So I'm going to help you formally specify this even odd bit string formula. So Q for that one is even odd. Those are your states. And then you have the start state, which is a special member of Q. It better be a member. Q naught is you start out even when you haven't taken anything yet. That's all. The input actions are the kinds of things that you could say. You could say to the state machine either a 0 or a 1. Those are your two inputs. See how this all is making sense? And then accepting states are a subset of your states that accept things. Like, okay, I'm looking for even numbers. I'm only going to accept those. I will not say that I accept the others. So my accepting states, you can have multiple. In this case, it's just the even state. You see that? It's really not too bad. The hardest one is the transition function. And this is what it does. It's called delta. It's like changing things. It's moving you around. That's why we call it delta, I think. It takes the current state that you're at, current state, and then it takes an input, and then it takes you to a new state. That's all. Does that make sense? So you have to have the current state that you're at, then you have an input, then you have the new state. So this is the idea. The delta function, if I can write it in terms of inputs and outputs, because that's what a function is, right? It takes some inputs and it gives you back an output, right? If you're in the even state and you get the input 0, you stay in the even state. See that? If you're in the even state and you get the input 1, you go to the odd state. That's what the function will give back. Okay, this is your input. That's all. That's the transition function. If you're in the odd state and you get a 0, you go back to even. And if finally you're in the odd state and you get a 1, you stay in the odd state. Okay, so that's your transition function. Accidentally put one too many of those parentheses, and this is how you would define it. Okay, it's really not too bad. Hopefully you see why each of these little pieces is very important in specifying the full state machine, and that's how you can talk about it in math and maybe prove things about it. It is all sets all the way down. That is what math is about. Okay, so finally, let's give an example of all this, and then I'll talk about the midterm, and we'll be out of here. So, I want you to read this question and try to do it. Okay, so give some output of each of these finite state machines. Dun, dun, dun. Give the final state that they are ending in. Sorry, not the output. And yeah, just tell me. Follow these state machines. Okay, so the first one's 1,000,000. Let's start. Let's do FSM1 here and FSM2 here, maybe. Can I move these over? Yeah. 1 0 0 0 1 1. Quickly, we start here. 1 0 0 0 1 1 B. Finite state machine 2. 1, 0, 0. Oh, sorry. It's not A anymore. My bad. 1. There we go. 1, 0, 0, 0, 1, 1. Ho ho. So that's A. And B over here is not accepting, but A here is. So that one was not accepting, this one is accepting. Yeah, that's not too bad, I hope. So again, always start at the start state. Let's do this one. 0, and then 3 more zeros. That's D. This one is 0, and then 3 more zeros. 1, 2, 3. That's A again. Not accepting, accepting. 0, 0, 1, 0. That's D. We didn't like that one. It didn't accept it. Finite state machine 2, 0, 1. Sorry. 0, 0, 1, and then 0. Oh ho. We're in C now, right? And that one's not accepting. Okay. Last ones. So let's do 1, 1, 0, 0 on both of these. 1, 1, 0, 0. So we're in state C. And finally we're accepting. Yay. 1, 1, 0, 0 here now. 1, 1, 0, 0. We are in D and we are not happy. Okay, so that's all. Hopefully that's not too bad. It's just a picture form of things, and we like pictures, don't we? So that is all for these slides. We are done with algorithm analysis for now. I want to now talk about the midterm because it is week 10, okay? The midterm is week 12, just like I promised, and I'm sorry, because it's right after spring break, but at least you have more time to study if you wanted to. So let me pull up this page and I will be right back. Okay, let's do this. I also want to talk about the extra credit because that goes along with the midterm, of course. So on the modules page, I will eventually make the midterm 2 module available for you, and I will give you the midterm 2 info and the extra credit assignment first. The rest of these will come later, right? The actual link and then a review link. So let us go to the midterm 2 info page. Just like the last midterm, it's going to be between 2:30 and 5:30 on April 8th and April 9th. Okay, that is week 12, the week I told you about, and the Thursday and the Friday. Okay, 8th and the 9th are the Thursday and the Friday, and so make sure to start an hour and 15 minutes before on the last day to make sure you have the full time. Okay, so here is what the topics are going to be. All these chapters, I could have just said 3 through 7 and then 9, but I wanted to give them to you in order. Chapter 7 will be the last one that we consider on this midterm, and so homework 6 will be the last one because that one is on chapter 7. So all of that, and then lectures through week 10. Technically, I'm about to start a new lecture in the next one, a new set of slides on a different chapter after 7, so you technically don't have to worry about that one. Okay, so really this lecture was the last one that's going to be on the midterm. I'm not going to say week 11 just because that would be kind of evil. I don't want to make you study things that I just taught you. Okay, so it will have multiple choice again. It will have a lot of multiple choice, but I'm also going to include some short answer questions, especially for like chapter 7. I can imagine giving you questions on algorithm complexity and asking you to like write down what the actual complexity is, and maybe if you want partial credit, show your work, something like that. So yeah, again, it's going to be open book and open notes, so don't fret too hard about not having access to things. Just make sure not to cheat and talk to other humans, okay? So that is the midterm 2 info, and then let's talk about the extra credit as well. So just like last time, it's exactly the same amount of extra credit, make the review materials, okay? That's all. So do it for stuff that will be on this midterm, and everything that I explained in the last extra credit applies, okay? So you can do the similar kind of thing and get your extra credit points. So that is that, and this will be due. I actually want to extend the date. I think it was accidentally set wrong. I want it to be due right before the midterm, so let's make it the 7th, I think? What day was this supposed to be? Yeah, it's the Wednesday. So let's make it the 7th, right before the midterm, okay? That will be when it's due. And that is all I have for you. So do consider doing the extra credit. Make sure to study all these chapters and homeworks, and yell at me if you have any questions. So I think that's all I have for you, and I will now see you in the next set of slides.